Each experimental section has a floating desk associated with it to get rid of the vibrations. And this desk is ellipsometry. It's a manual ellipsometer, which is used to measure thin films and get the students used to measuring nanotechnologies. This bench is a dual set of experiments. It has a scanning piezoelectric interferometer and a fiber optic laser and various other lasers, and it is used to get the students used to laser diagnostics with a Fabry-Perot, scanning Fabry-Perot interferometer. Oscilloscope and the scan controls produce the control over the scanning piezoelectrics Fabry-Perot, and the laser diode controller controls the current and temperature of the unit during its monitoring of the piezoelectric. This is a laser interferometer for wavefront evaluation. The wavefront of the optic is compared to a standard, and we have a camera which goes into the student's laptop, and they can see the wavefront deformation and calculate the quality of the image wavefront from the system. Will be set up for the evaluation of the optics of gratings, optics of spectrometers, in which the students will evaluate various gratings, all right, like this, in the modes set by them on the table, all right, and they will be evaluated with a laser input. Laser comes from the other side and fed into various detectors to check the performance of the gratings, the various forms of gratings as applied to the design of spectroscopy. Okay. This is the holographic setup in which the students set up and make holograms and holographic interferometers. All right, it consists of a high quality, high coherent laser and various film backs and film capturing equipment, and we produce. All the students produce holograms and holographic interferometry at this point, and learn about holographic interference from the system. Again, it's a floating table on air, and the optical system here is set up preliminary for a Mach-Zener interferometer to check the stability, and then they change over to set up a holographic fringe measuring and counting, and they make their own holographic plates on non-liquid plate plastic holograms. The floating table is set up for dual beam interference, and the students set up a Michelson interferometer with various sources, and with it they measure the coherence length of the lasers, sodium sources, mercury sources, and the performance of the beam splitter. They also break this down and make a Twyman Green interferometer out of it without this section to see the wavefront formulations off the reflected beams. For it, we have multiple sources, multiple mercury sources, and a fixed Michelson interferometer and a laser feed. Devoted to spectroscopy, in which we have a 1/4 meter and a 1/2 meter Turner spectrum, in which the students will scan the mercury, hydrogen, helium, arcs, and look at the results on atomic spectroscopy. They will then go to a longer 1 meter single point spectrometer and look at the spectrum of hydrogen and mercury, especially the mercury 198. They will do that with a detector amplifier into a lock-in to a scope, and they also have a digitizing oscilloscope to scan with, so that they can check the performance of the spectrometer as they learn how to run spectroscopic analysis. 6 meter Fourier optics bench setup, in which the experimental laser beam, we go through various Fourier lenses and produce various diffraction patterns diffraction patterns, and the analysis of the patterns is concluded by a scanning microdensitometer, which scans across the pattern coupled to an A to D converter, which then the students then check the intensity profiles for various structures against the Fourier transforms. This is a 3-meter classical nodal slide optical bench with infinity collimator and various lenses for the students to test and check for all the properties of the lens and check for aberrations. And we also have a Tor Labs camera adapted to it, such that in the proper system, the system can be used to measure the square wave MTF quality of any number of lens samples in the system. Okay. We have a camera tri-microscope in which the students can set and measure the patterns used and size of the patterns used on the Fourier bench and confirm the sizes that they are being used to diffract with. This is an open case half-meter array spectrograph, which the students build, align, and then analyze the spectrum and calibrate to get used to instantaneous spectral analysis of sources and lamps, which we'll produce here, and the array is on this end. It's an optical test station and a cleaning station and a metrology station for the cleaning of optics, the measurement of the optics against standard flats and curves, and we have cleaning supplies, cleaning methods, and spherometers and micrometers, verniers, for measuring lenses to check their performance on the optical bench against the measured values of the lens. Spectroscopes for the basic evaluation of optical properties, including angles, prism angles, as well as the index of refraction measurement, and for some diffraction experiments. The transmission of information in any system is optical.